Hello, good afternoon, good evening. This is structural analysis made fun and easy. This is a late video, but this is flexibility method in action. This is a second part of the video. Just to explain, this was a part video to flexibility method in action. My reference, example 03, it was the problem with the continuous beam with 3 spans. So I was trying to work out how he worked out the deflections, because if you remember, he has VB0 equals 8.8 over EI and VC0 9.08 over EI, and I was just wondering how he calculated those. So this video is on this was, remember, the release beam. It had 2 supports, one at B and C, one each at B and C, and then we're going to remove the supports at B and C, and then you've got to find VBO and VCO, which is the deflection at B and deflection at C under the loads. How has he calculated the deflections? How did he get the values for the deflection at B and deflection at C? So if you remember, it was a 3-span beam, 6 kilonewton point load, 10 kilonewton point load, 12 kilonewtons per meter UDL on the last span. So my diagram here, I've just redrawn it, not to scale. The indicative for deflection, there's a little bit more on the right hand side because you've got more load on the right hand side. So it makes sense that he's got VB. It makes sense just looking at that. Deflection at C is more than deflection at B, but I still don't understand how he got those values. So how was he calculated? So the first thing I realised was that he's using, in his deflection, he's using the units of newtons and meters, kilonewtons and meters. He's using the units of kilonewtons and meters, and not newtons and millimeters. Because I tried a few times using newtons and millimeters. Obviously, you don't get anything like what he's got. So let's just quickly consider that. Consider if it was only a point load of 10 kilonewtons at the midspan, then we know that the deflection at the midspan would be PL cubed over 48 EI, and we would have in such case we would have P equals 10 kilonewtons, and L cubed would be 3 meters cubed, which will be 3 times 3 times 3, which is 27 meter cubed. So therefore the deflection at midspan would be 10 times 27 over 48 EI equals 270 over 48 EI equals 5.65 over EI. So this looks right. This looks comparative to his values here. He's got a little bit more than mine. He's got a little bit more than that. So if you just had the point load in the middle of 10 kilonewtons, that would be 5.65. So that would be kilonewton meters over EI deflection. So that's obviously how he's worked it out. So hope this. I'm just learning on a learning curve, like you guys, on some of this stuff. Just found it hard to follow the example in the book. It's not very clear at all. So hopefully this helped. First step to clarifying how he worked out those values. So the next thing we need to do, I need to find out exactly how he did 8.8, 9.08, and then I'm going to work out the. I think I started to do that in the last video, but how to work out that you've got to put the unit load at B and then find deflection at B and C, and then a unit load at C and find deflection at C and B. But obviously it's symmetrical, so we'll go over that into the next video. Please tune in for part 3 and more for the clarification of the actual values. Thanks for watching. Please like this video, subscribe to the channel to let me do more videos on structural analysis. Thanks.